Hi everyone, here's yet another nice and easy problem from a Hungarian math contest that I'm going to be solving in this video. Here's what the problem says. Let A1, A2, A3 up till AN be an arbitrary arrangement of the numbers 1, 2, 3, 4 up till n. So these numbers are in sequence and these numbers are some arbitrary arrangement of that sequence. Prove that if n is odd, the product, which is a1 minus 1 times a2 minus 2 times a3 minus 3 all the way up to an minus n, this is an even number. So we have to prove that this product is even given that n is odd and given that the AIs are some arbitrary arrangement of the first n natural numbers. So as always, let's take some small concrete numbers to investigate this problem further. So given that n is odd, let me take n as 3 to begin with. So my naturals in sequence would be 1, 2, 3, and let me take some arbitrary arrangement of these numbers, which will be my AIs. So my AIs will be, let's say, 2, 3, and 1. And now if I look at the differences, a1 minus 1 is 1, a2 minus 2 is 1, and a3 minus 3 is minus 2. So if I take the product now, this is an even number because I'm getting this even integer in the differences. Let's take another example. So let me now take n equal to 5. So my naturals in sequence would be 1, 2, 3, 4, 5, and now let me take the AIs as some random arrangement of these numbers. So I'm going to take A1 as 4, let me take A2 as 5, A3 as, let's call it 2, A4 as 1, and A5 as 3. So let me take this arrangement 4, 5, 2, 1, 3. And now if I look at the differences again, what do I get? So I get A1 minus 1 is 3, A2 minus 2 is 3, A3 minus 3 is minus 1, A4 minus 4 is minus 3, but A5 minus 5 is minus 2. So if I take the product now, while the first 4 multipliers are odd integers, the last one turns out to be an even integer, and yet again I will get an even number as the product. So it seems like no matter how I arrange the naturals, no matter what sequence I take, I will always end up with at least one even integer in my differences, and that will make the product even. And this is what I'm going to try and prove now. Okay, so our product is a1 minus 1, a2 minus 2, up till an minus n, and we have to prove that if n is odd, then this must be even. Now suppose what would happen if all of these multipliers were odd. So suppose that all these multipliers, all these factors were odd, then a1 minus 1 would be odd. What would that mean? That would mean that a1 itself is odd plus 1, so that would mean that a1 is even. Now, if I do the same thing to the next multiplier, which is a2 minus 2, if a2 minus 2 is also odd, that would mean, what is the parity of a2? a2 minus 2 is odd, which means a2 must also be odd. So a2 is odd. And continuing this way, a3 minus 3 is odd, which would mean that a3 itself is even. So a3 is even. So what I'm concluding from here is that the parity of the AIs is alternating. So a1 is even, a2 is odd, a3 is even, all the way up to an. But remember that n is odd. So once again, if I take a concrete example of n, let's say if I take n as 9, then the first n natural numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is my sequence of the first 9 natural numbers. How many of these numbers are odd? So 1, 3, 5, 7, and 9. These 5 numbers are odd, and how many are even? 2, 4, 6, and 8, they are even. And so the number of odd numbers in this is one more than the number of even numbers. And that is actually obvious. It should be so because up till 8, the odds and evens will be the same, and then the ninth number is odd. So you have one more odd natural number than even natural numbers. But if you look at this pattern, you're getting A1 is even, A2 is odd, A3 is even, and so on. And once again, if I just use the concrete number 9 here, and if I continue this pattern up till 9, so A9 minus 9 is also odd, which means that A9 will be even as well. So if I look at this sequence of the AIs, which of these will be even? So A1, A3, A5, A7 and A9. So A1, A3, A5, A7, A9 will be even, and A2, A4, A6, A8 will be odd. So in this sequence, I'm actually getting 5 even numbers and 4 odd numbers. But the AIs are just a rearrangement of the numbers from 1 to 9. So I should still have 5 odds here and 4 evens here, but I'm actually getting 5 evens and 4 odds, and that is a contradiction. And that means that my assumption that all of these are odd, that simply can't happen. And therefore, at least one of these multipliers is even, so the product should be even. So that's one way to solve it. Quite elegant, quite nice. But there's actually an even more elegant way to prove the same thing. And this is the approach that I actually like more. So in this approach, you once again look at the product, which is A1 minus 1, A2 minus 2, up till an minus n, and given that n is odd, there are n multipliers, an odd number of multipliers in this product, and now you just look at the sum of those multipliers. So look at the sum of those multipliers. So let's call that S. So S will be A1 minus 1 plus A2 minus 2 plus A3 minus 3 all the way up to an minus n. So you collect the AIs together. So you get A1 plus A2 up till an. So these you collect together, and then you collect the naturals in sequence together. So minus 1 plus 2 up till n. And now here's the beautiful thing. Because the AIs are just a rearrangement of the naturals, this sum will be exactly the same as this sum, and therefore the total sum of the multipliers must be 0. And what does that mean? It means that the sum of the multipliers here, and this is an odd number of multipliers, their sum is 0. And an odd number of numbers summing to 0, which is even, that cannot happen if all of them are odd. If all of these multipliers were odd and you have an odd number of them, then their sum would have been an odd integer. But because the sum is 0, which is an even integer, it means all of them cannot be odd. At least one of them has to be an even number. So one of the multipliers in this product has to be even, and therefore the product is even. So that is the second argument. I find it much more elegant, the first one. But let me just quickly recap the two arguments. So in the first one, you essentially start by assuming that all of these are odd, and then you look at the parity of each of the AIs. So A1 minus 1 is odd means A1 is even, A2 minus 2 is odd means A2 is odd, and so on. And you find that A1, A3, A5, A7, that sequence is even, and A2, A4, A6, so on, that sequence is odd. But that does not line up with the number of evens and odds you will have up till n. For example, if n is 9, you would have 5 odds and 4 evens, but this gives you 5 evens and 4 odds, and that does not line up. So that was approach 1, but approach 2 was even more elegant, where we just look at the sum of the multipliers, and we found that sum to be 0, and we basically concluded that all of those multipliers cannot be odd, because the sum of an odd number of odd integers must be odd, but this sum is turning out to be 0. So at least one of those multipliers must be even, and therefore the product must be even. So I love this second argument. It's very elegant. It concludes the whole problem in just one line. I hope you liked it too. Once again, if you have any comments or suggestions or alternatives to solving this problem, do share in the comments. I would love to know. Thank you.